So today's topic is embedded systems. Just a moment, I check that there. Yep, it works. Embedded systems, meaning what kind of considerations you need to take when you are actually designing a, for example, handheld device or something like that with limited resources. If you have a PC, then you always have the mathematics core processor that actually make things swing. But on the say lower performance computers like any mobile, then you need to take some considerations. And the first consideration you need to do is to have some sort of idea of the performance. Okay, this actually should be done before buying the or selecting the hardware. But okay, if you have selected hardware, then you have nothing else to do. You just work with it. One specific command actually is well specific for the digital signal processing systems is the multiply accumulate operation, which is the basics for calculating any filters. Okay, in PCs actually there are max usually also on the graphics card. But on the other hand, there are also, these are multi-core processors. It could be that one of the processor cores is dedicated to a digital signal processing kind of systems as well. If you are going to do any games and that kind of stuff, you are actually needing the same operations to do all sorts of ray tracing and doing these fast graphics and game engines and that kind of thing. So that takes a lot of calculations. And yes, actually the simulation of physics, which is part of the game engines. Okay, there's a different equations that are solved. And okay, one way of solving it, you basically have the just formula there as a IIR system. Of course, you can make it as a transfer function and then basically run the whole system as a transfer function, and then it comes back to the fact that you need multiply accumulate operations. Okay, and yeah, for example, direct FIR calculation, which is just the that formula there. So basically, we have the impulse response convoluted with the input signal as a code for single time step signal. You actually just run it on a loop like that. Good. What else? So, for example, if you have 100-point the FIR filter, you need to have quite a lot of calculations. So it's about 100 multiplications and accumulations for each output signal. It takes some computing power, but well, nowadays we have a lot of it. We used to have a time in good old days when Texas Instruments and analog devices actually both came up with really fast digital signal processors. Now they are becoming, say, rare commodities because of these mostly ARM processors. Multi-core ARM processors can do quite a lot of things in addition to the signal processing. And for example, there are some ARM cores that has the special digital signal processing, the instruction set, and optimized for multiply accumulate operations. Okay, so Mac in embedded processors. So basically how fast it goes depends highly on the processor architecture. Floating point implementation would always be the easiest way to go on the calculations and software, but on the other hand, if there is no hardware for the hardware acceleration for floating point calculations, then you are losing a lot of power for the software implementation. But as I said, modern processors usually have a Mac unit. Some assembly may be required. So it's like IKEA furniture, you buy it from shop, but you still need to assemble it. Hardware, software, floating point arithmetic. Okay. If you compare, well, there are not too many 8-bit processors on new designs anymore because they actually, ARM and others. The processors are cheap. Processor cores are cheap. But anyways, if we had then single precision floating point multiplier accumulate in 8-bit processor would take thousands of instruction cycles. On 32-bit processor without floating point hardware, that would take hundreds of instruction cycles, maybe actually closer to 1,000 or a little bit more than that. Okay, so and that's a single precision floating point. It takes a lot of time to calculate by software. There are some fused multiplier at acceleration available, meaning that there can be some special hardware to do floating point Mac in single cycle without rounding. Okay, and then basically if you really need fast performance, then there are still available the digital signal processors and parallel processing, pipelining, all the ugly stuff to do several Mac operations on a single cycle. But those are special kind of things. Okay, then let's go back to this business. Since if it takes so long time to do these floating point arithmetics, then actually we may need to go and do the fixed point calculations, meaning we have to also quantize the parameters. Quantization of data, it's not that bad effect as long as you have enough of bits to represent the data. But then the quantization of system coefficients, filter parameters, can actually lead into real problems. This example here has this blue line showing the calculations which are done for the filter on floating point arithmetics. Then we have the 16-bit arithmetic is the red one. It also already starts deteriorating from the optimal one, but the 8 bits it's still low pass filter, but I would say that's useless. So okay, it does not fit into the filter requirements anymore. And actually, in that case, if you have a pole close to the unit circle and you quantize the coefficient, it can actually move that pole outside of the unit circle, and then you are in big trouble. Your filter doesn't work. Okay, some things you can do to reduce these rounding errors due to the quantization of filter coefficients, and there you need to actually start thinking of system combinations, and especially how to break the system in second order systems. Do I have the picture? No, I don't have the picture. Maybe I'll draw a picture next to this nice green green phase here. There. I leave this one because it's so beautiful. It's like watching a mirror on the morning. Okay. I don't kill anyone here yet. Okay, so let's see if I can get any one of these actually do anything here. No. No. Yeah, but the red is, where's red? I don't see the red anymore. Someone took the red. Is that the whiteboard marker? Okay, good. No, it's not good. Green, okay, green is okay. So there we are. So we have a zero pole plot. Typically, system, low pass filter, IIR, they look more or less like this. So we have this flat passband done with these poles here, and then the good, nice, wait a minute, maybe that should be there. Okay, the stop band attenuation done by these zeros. Okay, how to break this one into second order systems? It's easy. You take, for example, these zeros and these poles. That's a second order system. Then you actually take these zero and pole pairs as second order system, and then this one is the third second order system. So you can actually simply make system 1, 2, and 3 by taking pairs of pole and zero as the defining parameters for the system. And of course, then you need to also have some gain for each system, basically to keep the total gain for the passband as unity. So SOS1, gain 1, SOS2, gain 2, SOS3, and gain 3. Okay, how come this one actually changes anything or makes systems easier to calculate? Well, let's think of a system, for example, like h of z equals 1 minus 1, and let's see. I'm thinking of something here. Okay, let's make it plus to some very high exponent here. For example, well, if that is 1, then we have basically, okay, well, how does it go? 0, 1. Some n, big N. Think of the what is that? Is it called Fibonacci triangle or whatever that is? We have the numbers 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. You remember this one from the high school mathematics, right? How to calculate this kind of the coefficients for the or scaling factor for each. When you are here at the around 100 order, which is still say you can calculate those. Okay, Then you have the difference between the highest scaling factor and the smallest scaling factor in order of 100. So 2 decades, meaning that if you are having any bits, other bits, you have 8 system, then basically you have only one significant bit on that one anymore. So you don't have basically any room for the error anymore when you have that kind of system. But if you have it on cascaded, you keep the cascaded second order system, you keep these coefficients within the same order of magnitude. So you don't get that much calculation errors, or quantization errors. Okay, and that's basically an example of that one. So we have the floating point again, 8-bit arithmetics, and with the direct form, and then we have the 8-bit arithmetics but second order systems. And practically this 8-bit the arithmetics on second order system actually had the same performance as the floating point on this example. Same thing actually for the IIR. So in here I have the floating point 8-bit, the direct form, and 8 bits second order systems. Basically there's only small scaling difference between the second order system performance and the floating point, while the 8 bits without the second order system, so direct form, actually gives you already useless amplitude response. Okay, that's the theory part. There's also lots of mathematics, but that actually goes into statistics and it has nothing to do with the reality. You cannot forecast for what kind of thing you can get. That's something you need to basically explore by testing. And that's why we go next to the and start the MATLAB.